Welcome everyone out there in audio land. We're here for another episode of Pints with Ayre. And today our topic is going to be digital clocks. With me to my left is Ariel Brown, our chief engineer and designer, and also Ryan Berry, our CEO and technical expert. I'm Brent Heffley, I'm the marketing and sales manager. So let's start off with Pints. What have we got in our pint glasses today, gentlemen?
We have Upslope Brewing. It's a new one from them, German style Pilsner. Upslope has I would say, one of the other breweries that Ayre has the most connection to. They used to be a couple buildings down from us when we were at our previous location. And so we spent a lot of time there after hours.
I remember a few lunches there.
Yeah,
that came up with some great marketing ideas.
Yeah, we had a lot of meetings there, even with colleagues. Jim White would come in from out of town, or friends would come visit us at Ayre, and we would almost always go over there for lunch.
It was very handy, very, very handy. Well, I couldn't find it out here, but I have one of my favorite breweries, Boneyard IPA, an IPA from them, Hop a Wheelie. Gotta love it, a little Hunter S. Thompson-esque graphic.
Here's a little more exciting of a can than ours. This is very, down to business kind of can.
I kind of like those basic retro cans. Like, it's a new retro, and they're coming back, and I appreciate it because some of the artwork just got ridiculous. Like some of it was just silly. And,
sure.
Yeah, it's like put more on there just for the point of putting more on there.
Yeah, no, Upslope is committed to doing cans only. They do not do any glass. They're pretty.
Nice.
They're a fairly staunch philosophy about why cans are the best idea.
Yeah, you know what? It's interesting because and this is way off topic, but like how much energy goes into recycling aluminum versus glass, and
Yeah, I mean, then you don't have UV problems with cans that you do with bottles, so it makes sense.
Right.
Yeah.
They're also
throw an empty can at somebody on stage, you don't really hurt them.
Yeah. They're also far more packable, and they're easier to pack in and pack out.
Right.
As far as outdoor stuff, which is one of their.
Oh, for sure. Yeah, that's a really that's a great reason right there to have aluminum.
Yeah.
Cool. Well, let's get to our audio topic and talk a little bit about digital clocks. When you search Google the first time for digital clocks, you get a bunch of Walmart ads for digital alarm clocks. You search it again for audio DAC digital clocks, and you get a couple more relevant things, but there's not a crazy amount out there that goes into it, and probably because it's pretty technical. I would imagine. I think what most people in the audio industry know about digital clocks is you need one. They go with your DAC or your CD player, and somewhere in there's a crystal that oscillates that is, the basis of the clock to some degree.
Yeah, well, it could be crystal. But so back up just a little bit. So basically, any digital circuit requires a clock to provide it basically a timing reference. It's basically what basically initiates every operation in any digital circuit is basically a clock, and very specifically a clock edge. Every time there's a rising edge on the clock, and so a clock is in the most general term is basically a very consistent square wave signal. It is an analog signal because any actual signal has to be generated in the analog domain.
Right.
It can be interpreted digitally, but so a clock is basically a timing reference.
It gives it a sense of time. Otherwise, there'd be nothing that tells a program that it could run.
When to run, when to do anything. Yeah.
You try to do everything at once, and obviously that doesn't work.
Yeah, that would be bad.
Right. So when we're talking about audio circuits, the clock becomes very important when we're talking about conversions, when we are changing domains. specifically digital to analog or analog to digital, that clock becomes the most critical thing, because you know, in when you're in the analog domain, you know, there is no time reference. It is just, you know, it is just a infinitely continuous waveform. And so when we, you know, want the convenience of going to the digital domain for transport, for storage, you have to convert to digital. And so if it has to be converted at a very, you want it to be converted at a very consistent rate, and then converted back at a consistent rate to ensure that the beginning analog and the resulting analog are the same. If you have inconsistencies in that timing reference in that clock, then you will get, which is what's known as jitter. Then that will create ultimately distortion of the analog signal. It will not, what's reproduced will not be exactly like what it was originally.
Right.
Now, and that's usually a fairly small scale, but when we're talking about high-end audio, it all matters.
Everything counts.
For sure. And the jitter is something that's obviously been a topic. You know, how much jitter does it have? You know, how is that measured? And I know from some talks before that there are different ways to measure that, and it's not an absolute science of how you measure the jitter, you know, and how you quantify that, which can lead to different specifications.
Right. Yeah. There's you know, you can measure it as phase noise. You can measure it as you know, some people will measure it as a picosecond or picosecond jitter spec or femtosecond or whatever it is, and that's more or less measuring the absolute maximum possible deviation from the theoretical ideal exact transition time. How much does it deviate from what you want it to? Or there's phase noise generally, which is just a different way of looking at that. And so, but if you back up, so when we're talking about first generating a clock signal, it's certainly a high quality clock. You use a crystal, and there are different types of crystals and just types of oscillator circuits. You can build your own discrete circuit. You can buy an off-the-shelf can. You can buy a cheap off-the-shelf oscillator. You can buy ultra expensive, hundreds of dollars, oven-controlled crystal oscillators. There's a wide variety in qualities.
Right, and there's the quality in that, and then there's also, so we're talking about the crystal, but then we're also talking about the temperature control of it, because the temperature, that's
an option,
right? Because the temperature can have an effect.
Yeah, temperature has an effect. The voltage, the power supply, is maybe one of the most overlooked parts of it and most critical. The type of the crystal cut is a big factor, and so depending on what type of oscillator you're trying to build, there's different types of crystal cuts you want to use.
Right.
So lots of factors, and so as I kind of alluded to, the power supply is probably a bigger factor than a lot of people think. So you can buy a very expensive off-the-shelf oscillator and throw a pretty crummy power supply on it, and it's going to be a pretty crummy clock signal. You can buy a pretty affordable off-the-shelf crystal oscillator and use a really good power supply and get a really good clock signal.
Well, that's really interesting too, because you could have a crystal oscillator, as you're saying, that has great specs, great data, feed it up, a mediocre power supply, and just ruin that, or not take advantage of it. That's really, really interesting. Because the power supply obviously costs money, but then it's a balance, like how much are we spending on the power supply, how much are we spending on the crystal, what's that add up to, for the price of the product, especially when you're trying to make high end that's reasonably affordable, like
Right.
we're trying to do.
Yeah.
All those pennies count. Um,
Yeah, and I think going way back in history, I know Charlie was way better at kind of audiophile company history.
mm-hmm.
But so like I'm pretty sure it was Wadia. They I think their oscillator circuit, they actually used a battery as either the power supply or the power supply reference for their oscillator, and that was was a fairly innovative idea because the battery is theoretically one of the lowest noise
Right.
power supplies.
Yep. Yep. Yeah, that's a cool idea.
Yeah, I've thought about that many times. There's some drawbacks to using a battery as part of the circuit, but
not if we get a new Tesla battery. If we get a new Tesla battery for that R series DAC that we're going to make sometime,
right.
that would be awesome.
Yeah,
I have to put their logo on the front of the faceplate though, which wouldn't be so awesome. But anyway,
right. So let's see. What else we talk about clocks? So, so obviously the goal is to make a perfectly consistently timed clock, so that the that the square wave that has exactly the same timing between each edge. So there's that, but there's also then the actual shape of that clock waveform, which is ideally a square wave.
Oh, right.
Now in real life, you can't actually achieve a perfect square wave because we're talking about analog here. We're not talking about theoretical digital, which is just would be a perfect square wave. We're talking about real world analog. You can't actually achieve a perfect square wave. So there are rise times, which is one of the big factors. And so in general, you want the fastest rise time possible so that it passes through the threshold region as fast as possible so that there's the least possible variation in when the whatever circuit you are clocking interprets it has changed states.
Uh-huh.
That clock rises slowly. It then has a chance to when the DAC chip or the microprocessor or the DSP, whatever it is, whatever you're clocking, it has this window of when it detects a transition from low to high.
Uh-huh.
And so if the clock signal is slow rising, and it passes through that window, there's basically a big window of kind of variability where it can switch.
Mm-hmm.
And so one way to address that is to make the clock rise time as fast as possible so that its time passing through that window is as short as possible to make that to basically reduce that variability in that jitter effect.
Okay, so what's the most important component to make that happen? Is it the crystal itself, or is it a
No. I mean, a crystal itself is basically generating a pure sine wave.
Uh-huh.
The crystal works. You basically apply a voltage across the crystal, and there's basically more or less almost tension in this physical, quartz crystal element,
right?
And you actually induce it to oscillate. So so electrically, it is essentially creating a pure sine wave.
Okay.
So then the oscillator circuit around it, both the parts that you apply voltage to it, and then a receiver circuit, so you actually convert that sine wave to a square wave with essentially amplifier circuit.
Okay.
More or less. So you're basically saturating, you're basically clipping right. A low amplifier.
Okay.
And you either buffer that or you output that, and it's more or less a square wave.
So it's that circuitry around the crystal that's really the critical piece at making the best square wave possible.
Yes. As far as generating the square wave part of it, yes. Oh, it's funny. We just received an email from one of our crystal suppliers, or from our oscillator.
Nice. I love that we have a crystal supplier. Do we have a
well timed,
like a little sage supplier to go with the crystals and all that?
Not those crystals.
Not those crystals.
No, we
the
don't.
on the,
Not, it's not quartz.
Pearl Street downtown in Boulder.
Right.
Yeah. So so there's the oscillator circuit itself. So you have the crystal, and so the crystal itself matters, and so crystal itself it can have a natural Q, and the circuit itself has a natural Q, and so the higher the Q, typically the higher quality clock is going to generate. And in various products that we make, sometimes we do our own discrete oscillator circuit with discrete logic gates. Sometimes we will use an off-the-shelf oscillator in a can. And they both have advantages and disadvantages, both in terms of cost and in terms of quality and in terms of and so even the cheaper off-the-shelf versions, they have some advantages because they are actually built in this little box, so they actually are pretty well shielded. So they have advantages as far as radiation and actually even rejecting noise from the outside.
Right. Yeah, that makes total sense, but I hadn't really thought of that before about external noise affecting the oscillation of the crystal, which of course it would.
Yeah. So then, for us, one of the next factors we consider in actually using and placing an oscillator. For us, we always place an oscillator as close as physically possible to the DAC chip or the ADC, whatever that conversion chip is, the most important point in the circuit. So we place it right next to it, pretty close to them.
And that's so that jitter it reduces the jitter in terms of that transmission length?
Well, yeah, I mean, it just reduces any possible, because if it's far away, you have to send that signal along. You have to send
longer traces or wires or whatever.
Sorry?
Longer traces or wires or wherever it's coming from, if it's internal or external.
Yeah, and so it's more difficult to keep the signal integrity high when you have a long way to travel. When it's right next to it, you can't get any better signal integrity essentially.
Right.
And so, and then whenever we often use the same clock to run other parts of our circuit, but those parts are far less critical. They're just logic parts, so it's not the data conversion.
Right.
It's the most important part.
Right.
Now, it's kind of the dichotomy is that when you're talking about fast rise time signals, in some parts of the circuit, you actually try to avoid that because that's the faster the rise time, the more EMI radiation you are generating.
Oh wow. Okay.
Right. So, which is another reason why it's good to have that very, very close to the clock chips, so that there's no trace length to actually radiate that. And then we actually try to control the clock routing to other parts of the circuit and actually try to reduce rise time to actually reduce noise generation from those parts of the circuit.
Right. So this is part of the reason that we don't do external clocks or have clock in puts on our products.
It's pretty much impossible to maintain the same quality of signal integrity of the clock from any external source. You can do a good job of it. You can do your best, but you're never gonna be as good as having the best clock you can make right next to the converter chip.
Right.
You just can't do it.
Great. So with the clocks, there are different clock rates. There's a 44 and a 48 kilohertz clock rate. And I know we address that by having two separate clocks. Not everyone out in the world may know why we do that or why it's important. So you want to delve into that a little bit, Ariel?
Sure, a little bit. Yeah. So the most commonly known clock rate would be that we used on CD was for the 44.1 kilohertz, and so that was the standard adopted by, I believe, Sony at the time. And so then everything that is the CD standard. And that was adopted for a long time and for a lot of things. When DVD came out, I believe is when the second round, 48 kilohertz.
Yeah, it was designed to better sync with video, is what it was.
Right. And so and everything's kind of based on multiples of that now. So
right. So you have 44,
a lot of 48 based. You see 96 and 182 and 384.
Yep.
So that is the base sample rate.
Mm-hmm.
Now, as far as a clock rate, that's as far as like a master clock goes, you'll see clock rates much higher than that, because the actual bit rate of those sample rates, because sample rate is basically how often the samples are generated. But then there's usually 24 or 32 bits per sample, and then you do a left and right channel. So often you do at least 64 times the base sample rate will be either the bit clock or the master clock, and oftentimes the master clock will be much higher than that.
Right.
So it's like on some of our products will either have roughly 22 or 24 megahertz, or 45 or 49, or 90 or 99 megahertz.
Right. So the clock rate in the machine starts really high, and then it's brought down to whatever the sampling rate is.
Yes, because the master clock, the master clock that we generate, with the actual oscillator, that has to be much higher to actually do all the operations.
Uh-huh.
The sample rate, that's more of that doesn't relate to any clock, although there's the word clock, which is a division down of the master clock.
Right.
But that's not really a clock signal that you really see.
Mm-hmm.
So when you have a DAC, you will need to handle both those base sample rates, 44 based or 48 based sources, either from network or computer or a disk. And so we choose to use two separate clock circuits, one that generates 44 based and one that generates 48 based. And then we will typically turn off the clock that's not used, so that it's not generating noise or power supply and corrupting the other one, because they're not nicely related clock rates.
Right. Yeah. You can't translate one to the other.
No, not without a really complex PLL, and that just creates more problems ultimately.
PLL is phase lock loop for those?
Phase lock loop, yes.
Yep. So when you do so that's what we do. We do two separate clocks. Obviously, if you're building a $1,000 DAC or a $400 DAC, you're not doing two clocks most likely, or they're both really cheap clocks. So
most likely not.
Is it one frequency, and then you're just saying, okay, we're going to do the best we can with CD, and then we're going to let the 48 kilohertz rate just be off slightly, probably, or vice versa?
No. Most commonly now is that you actually use a clock that is neither of those. Use something like 100 megahertz or 50 megahertz clock,
right.
and then you actually asynchronous sample rate conversion. Either of those frequencies, either the sample rates, I mean.
Okay.
And then you can essentially create new data that aligns with your clock rate.
Right.
And the biggest thing is to make sure that you keep your base clocks the same. So, you don't want to bring in 48 kilohertz base sample rates and then try to convert it to a 44, because you get into weird math then, where then your DACs are doing estimating and they're, creating average data, and oftentimes, it'll just double up some sample to fit it in and everything, and that's not the right way to do things.
So if you're not into weird math, do separate clocks.
Exactly. You got to keep the purity there. That's the most important thing. Yeah. So it's real tempting for a lot of people to go and get their DAC, and they'll see the options through Windows or Apple, and they say, oh, the DAC can handle 192 or 384, and they'll just instantly click that highest number. Then they're playing CD sample rate stuff
Right.
through a player that doesn't handle the automatic sample rate switching on your DAC. So now it's doing this conversion from one into the other, and it gets into funny math, and it's never going to be as true as playing it at the base sample rate.
Right. So let me ask this broader question. How, all things considered in a DAC or a digital circuit, how important is the clock compared to, say, the DAC chip, the power supply, which you touched on earlier, or other aspects of that circuit? I mean, is the clock like ultra, 80%, of the value of that? Is it 20%, and the others actually make up more importance? Is it hard? Is it? I know it's a fluid question, right? Like
everything matters.
Yeah. That's not something I can quantify. I mean, I think it just depends on so many other things. I'll say it's important, and certainly up to a certain level. I think that, I think there's a certain threshold that again, just as with anything in high-end audio design, there's diminishing returns past a certain point.
Sure.
And so you can throw a lot more effort, a lot more money, a lot more parts quality at something, and it will improve, but it's starting to cost a lot to get a little.
Right, and at that point, you're probably better off putting more money into the power supply piece or
yes, absolutely,
other aspects of the player to make it everything it can be.
Yeah.
All right, great. Well, I think that's a good digital clock discussion. I think we'll touch on other parts of that circuit in future videos. The DAC chips maybe, some other pieces there. But if you have questions, there's stuff you want to know more about here. There's topics you want us to address in future things. Email us at pints@ayre.com. I'll put that up on the screen. And until then, cheers.
Cheers. See you soon.